All right. Hello, everyone. I'm Eberhard Hansis. I'm the CTO and co-founder of Webeto. At Webeto, we do strategic data analysis for hospitals, but that is not the main topic today because I'm not going to do a sales pitch here. I'm going to talk about geodata analysis in Python, and obviously that's like a huge topic. We could talk about that for days. My goal today is to kind of make you curious, to show you what's possible, and then maybe give you some pointers on where you can continue if you want to embark on that journey. So what are we going to do? We are going to do a little toy project in a demo, live demo. And the goal is find the primary school in Munich that has the most green space around it. So the most amount of trees, grass, and shrubs around it. And for that, we will need to work with vector data. We do that with a package called GeoPandas. We work with raster data with Xarray. And I just say a few words about scaling and parallelization. And then I want to spend a few minutes talking about my personal best practices for data analysis. All right, so now comes the exciting part. Live demo. What I've done here is just import some packages and define a few paths to my input file so I don't have to type them out. You are not expected to understand every little bit I'm doing here. All the code, all the slides are in a GitHub repo. You can look at everything again later if you want to. All right, let's get going. So the first thing I'm going to do is I'm going to load a little data set. Just a second. I'm going to load a data set with primary school data that I downloaded from OpenStreetMap. And you can see how I did that in the repo. You can look at that later. Oops. And you will see lots more typos. Okay, so what does that look like? This is the so-called geodata frame. In essence, that's more or less just a table. There's one like primary school per row. It has all kinds of attributes like the OpenStreetMap ID and address, other stuff. And it has also a geometry. So in a geodata frame in GeoPandas, everything has a geometry. So I can take the first school and plot that. There it is. That's a pretty school building seen from above. So this is defined by a polygon. Some of these schools are also defined by just single points. So I get a point. You see also here in the geometry column, some are points, some are polygons. Let's look at the whole thing. This is what it looks like. That's all the primary schools in Munich, and the things that are round dots, they are single points, and the other things are polygons. Now to work with that, we need to do a little bit of cleanup because on the one hand, having a mixture of polygons and points, that's not nice. And on the other hand, there's like buildings that are very close to one another that belong to the same school, and we want to unify them. So how do we do that? In the end, we want a single data set with a single point per school. So the way we do that is we first blow up each geometry by 100 meters. Then we merge all the geometries that touch, and then we split them apart again. And then we have our cleaned up data. Now to draw a 100-meter radius around a point or a geometry in lat-lon data, so this is latitude, longitude, that is not so simple. So first, what's useful is to reproject that to a coordinate system that uses meters as coordinates. So there's a magic number, 25832. And now we have our coordinates in meters. And this is a coordinate system that is fairly accurate in the region we are looking at. Now we can say I want my buffered schools to be my original schools. And I buffer them by 100 meters. Oops. And now I can plot that. Oh, come on. That worked much nicer when I did that. Anyway, so now we have all our geometries blown up by 100 meters. And now we can unify them. Let's take the unary union. That gives us just a single polygon that has all the schools in it, and then we will split it apart again into the single schools. We define a new geodata frame, and that has just this single unified thing, unified polygon. And then we explode that to get the separated schools. And now we again have our polygons, but now we have one polygon per school. We have merged the ones that are close together. And so they are nicely separated, they are deduplicated. And the final thing we can do is convert that and just get a single point. So we'll just take the centroid of each of these polygons. And now schools. We end up with our nice cleaned up list of schools. We have deduplicated them. We have merged the ones that are close together. We have a single point per geometry. Now, this obviously went very quickly. You can go back over the code later on and see what we have done. But you can already see here that we can do pretty complicated modifications and management of vector data in GeoPandas. And it comes with a lot of nice tools like for manipulating the geometries, for reprojection, for unifying shapes, doing differences, and so on. So that's a very nice tool. So now we have our schools. Now we need data about the green stuff, the greenery, and that comes as raster data. And that is from Copernicus. And you can see the queries for that also in the GitHub repo. So let me load the tree cover data here. Now, what is that? What we get here is a so-called X-array data array. So a data array is, first of all, just an array of values. It's like a matrix, but it also has coordinate axes. It has an X and a Y axis, and these have like numbers attached to them. So in the end, it's more or less just like a raster map of pixels, and each pixel has X and Y coordinates. So it's very much geared towards handling geospatial raster data. I can, of course, also plot that. And that's what it looks like. What we have here is we have tree cover between 0 and 100%. This is Munich. This is like some forest in the south. There's the Isar with lots of forest. There's actually the river running through it in the middle. Here's Nymphenburg Castle. So that's our tree cover. Now in X-array, we can do useful things like seeing the min value of the array, for example, which would be, this is the min value 0. We can see, of course, the max value is 100. And for example, the mean value would be 19% forest cover across Munich. That's interesting. These aggregation functions, they can do something else interesting. So we can say tree cover dot mean, for example. And we can say, I just want the mean across the x-axis. So now I get an array that only has the y-axis left over. I can also plot that. And now I get the mean forest cover for each y coordinate. So that is something like cheap zonal statistics for you. And you see that in the south, you have more forest cover than in the north. And it kind of fits our impression of that map. In the south, there's overall more forest cover than in the north. So X-array has all kinds of interesting and useful functionality for dealing with that raster data. What we want to do now is we want to count green pixels, so we have to binarize that, and we'll say that we call something forested or green if it has a tree cover of 25% or more. All right, that is our binary array. Let's look at that plot. Oops. All right, now it's binary, 0 or 1, and everything that is 25% or more forest now is called green. We have two more types of vegetation here. We have grassland. That's in a different file, raster.io. Let's look at that. So this already is binary, but I'll nevertheless say I call that grassland binary only where this array equals 1, because some of these arrays have 255 as missing value indicator, and I don't want that. So I say, yeah, it's truly only grassland if it has a 1 in that array. All right. And then we have one more type of vegetation. These are shrubs. And let's load that. That's called small woody features. And now this, let's plot that. This looks funny if you plot it because it has these 255s as missing value indicators. I'm not interested in those, so I would say shrubs binary is, I want only those pixels where my pixel value equals 1. All right, so now we have binary trees, binary grassland, and binary shrubs. By the way, if you were to look at the arrays here, you would see that they don't have numbers in them, but trues or false, because by stating these are binary arrays that are either it's 1 or it's not 1. So these trues or falses, they are they represent my my binary data. But if you plot them, false is mapped to 0 and true is mapped to 1. So that's why you see in color scale going from 0 to 1 here. Now these things here, up to here, we were working with so-called X-array data arrays, and you can think of a data array as something like a single map. I said that you have different coordinate axes here. Of course, you're not limited to X and Y. You also have a band coordinate axis here that it has just one value, because you could have like multiple bands of image data. Then you would have 3 dimensions. You could also have 4-dimensional data with X and Y, band and time, for example. So X-array can handle kind of any dimensionality for you, and you can attach coordinates to each axis. So you could have a time dimension that has years, for example, from some time series of data. So data array is kind of the data for one, I would just call that, for one map. We can also stick all these different types of greenery into a so-called data set. So we have to fill that with a so-called Python dictionary. We say what we call trees is our binary tree cover, and our grassland is our binary grassland binary. Now, the X-array is pretty smart. It sees that these two arrays trees and grassland, they have the same coordinates. So for the data set, it only stores one set of coordinates. So it more or less aligns the two maps. And now you have several data variables in there. If I now say something like greenery.mean, I get the mean per data variable. So I get both the mean of the trees and the mean of the grassland. And so these data sets, they are useful if you're working with several types of data that are all aligned kind of on the same grid. If you have like, yeah, like what we did here, you might also have height data or temperature or whatnot. Now let's also stick the shrubs in here. Shrubs equals shrubs binary. And now something funny happened, because now suddenly, so before we had 1612 by 1245 pixels. Now we have more than 3,000 and more than 2,000 along each axis. What happened here? The issue is that I intentionally downloaded the shrubs data on a different resolution. These two are at 25 meters resolution, and I downloaded the shrubs at 27 meters resolution. And now what Xarray does, it gives you in order not to lose any data, it gives you the union of the coordinates. So you have all the coordinates here that either appear in the trees and grass data or appear in the shrubs data. And that's not quite what we want. So I'll show you how to resample the shrubs data to the same grid as the trees and the grass data. And we can do that simply by saying shrubs resampled equals shrubs. And now there's a little magic thing. I explain in the notebook, in the repo, what happens here. Just leave that out now for time reasons. I have to remove the band dimension in order for this to work. And then I can say interpolate this like my tree cover data. And then it would look at the coordinates of the tree cover data and interpolate my shrubs data to the same grid. And I want that because it's binary data with nearest neighbor interpolation. And now I can have to do the binary thing again, but now on the resample data. And if I stick that back into, come on, it doesn't work like I expected to, right? If I now stick that into my data set, then everything is good. We again only have our original grid because we resampled the shrubs data to the same grid as before. Now there is a kind of a safeguard we could have put in to see that we didn't mess up our coordinates here. I can say here, I want to assert that the shape of my trees data equals my original data. If we had done that before resampling, then this would have kind of blown up and thrown an error message because we changed our grid here. And using these assert statements just to test things that we think should be true, that's a very simple and effective way of kind of injecting automated testing right into your analysis code. And I'll come back to that later on. So finally, now we have our three kind of types of vegetation in one data set. We want to now determine if any of these different types of vegetation is there. So we say any greenery is either trees. Now this thing here means or, so trees or grass or shrubs. About this. So now this is our kind of final pre-processed data set giving us all the pixels in Munich that have any kind of green vegetation on them. Again, this was very fast if you haven't seen any of this before, but you see again that X-array is very useful for working with raster data. You have resampling functionality, you have aggregation functionality, you can work with different coordinate systems, you can work with all kinds of file formats, netcdf, HDF5, you name it, plain text. So that is a very, very handy library. Now for the final part, I'm not going to type that out because that takes too long. What we'll do is we will see some errors. What was the name of my variable here? So that is a live demo for you. Schools points. Well, yes, okay. So what I'm doing here is I generate a new data frame. So now we are back in GeoPandas, back in the raster data, the vector data domain. I have introduced an empty column called green pixels here, where I want to count up the green pixels around each school. And I filled the geometry column with our pre-processed, cleaned school points. And what we will now do is we will run over this list. And for each point, we will look up the green pixels in a box around that point. In this array, we will count them and then fill them into that column. Again, if I type that out, that takes a bit too long. So I'll just paste the code here. So what we do is we run over this geometry column here. For each geometry, we extract the X and Y coordinates. Then we select the pixels, X minus a radius of 500 meters and X plus a radius of 500 meters, the same along Y. And then we sum the values in our selection, so the values in our green pixel array, and stick that into this column. Now, to be fair, this is not 500 meters in X because this is a Mercator projection, so it's actually less, but we'll ignore that for now. All right, that was quick, so that has run. Let's look at the results. So now we have still our point geometry here, and now around each point we have counted the number of green pixels in this pseudo 500 meter box. So what's left is to plot all that. For this, I have to first load the polygon showing Munich. So that is in a separate file here. Actually, you know what? I'll just skip the final plot because you can just look at that in the repo, and I'll rather spend some more time on the other topics that I have prepared. If you go to the notebook in the GitHub repo, you can see the final plot, and you can see, like, by coincidence, the last school here in the table, it wins. It has the most amount of green space. So here, this is our winner. It's kind of in the north of Munich. Anyway, so that was the very quick run through of what you can do with vector data and raster data in Python. Obviously, there's lots to learn. I also put scaling into the title of my talk. I'm not going to demo this. I'll just point you to here. These are links. You can also click them if you visit the repo later on. I'll point you to two projects that link X-array and GeoPandas to a library called Dask. And what Dask allows you to do is very simple and very, very powerful scaling. So it allows you to either scale to all of the cores in your laptop, And it also allows you to scale to a whole cluster of machines if you want to do that. It lets you work also on your laptop on larger than memory data sets. So you can have like a 10 terabyte map. And what Dask will do is split it up into little chunks and process them in parallel and kind of aggregate the results later on. It'll all do that for you. The code that you write doesn't really change if you do that on one core or if you do that on like a cluster of 250 machines. So that is extremely powerful. And it also allows you to work on multiple data sets. So you can say that parallelize this computation over this directory of 1,000 files. So that is super cool and very, very efficient. The same exists for GeoPandas too. So you can do like larger than memory data sets and parallel computing on vector data. This is in a bit more experimental state than the X-ray part. That is, the X-ray part is really, really mature. So if you're working with large data sets, Dask really is your friend. You can do great things with that. And now, finally, I want to spend like 10 minutes on some things that I would consider best practices for data analysis. And by this, I'm talking about best practices for serious projects. So if this is for a scientific publication, if it impacts business decisions, if it might go into products that you sell, then I think these should apply. Of course, you are welcome to disagree with me. If you're doing just toy projects, if you're doing exploratory data analysis, just do whatever you want. You don't have to adhere to that. The first and main thing is, if you want to do professional data analysis, take your mouse, put it in a box and blow it up, because you should never do manual editing of input data, and you should never do interactive data analysis in any type of professional data analysis work. I very much suggest that you do fully scripted processing only. So you write out your complete data analysis, including pre-processing of data, including the actual analysis, and including the plotting. And it should be such that you can delete all your output, all your pre-processed data, all your plots, push a button, wait for however long you have to wait, and everything should reprocess at the push of a button. That's how I think data analysis should be done. So clicking is forbidden. Why is that? You will run your analysis more than once, and you will be very thankful if the second or third time around you just have to push a button and you don't have to click through how many manual steps. You will run similar analysis in the future, and if you have written everything down as code, you can reuse parts of that, and you don't have to reinvent everything over and over again. Then a year from now, if you did things in an interactive fashion, you will not remember what you did, and you will also not write good enough documentation to remember it. If you have code, I mean, code can also be difficult to understand, but at least the code tells you what happens. And if everything is in code, then at least you can kind of follow along with the code and see all the processing steps. And finally, automated testing becomes possible. And I think that should be part of any serious data analysis project. That's not only me saying that. Here are two links to interesting. One is a blog post, one is a video of other people who are saying similar things in terms of reproducible data analysis. I suggest that you visit those later on. And what this also allows you to do is version control. Now, if you have never worked with version control before, you might have heard of GitHub. So this demo is on GitHub, and Git is a version control system. If you visit the repository of this demo in GitHub, that's what it looks like. And for example, now I see here that I have done 13 commits of this demo repository, and the last commit was some tweaks. And now I can see that I did some tweaks to my slides. I changed some lines in here. And if you have all your data analysis in code, you can see all the changes that anybody ever made to it, and that can be very, very useful. So it gives you version code, but also it gives you diffing and merging. What that means is you can see differences between changes in the process, but you can also merge changes that your colleagues made. So if you've ever tried to merge changes between two Power BI notebooks or between two Excel files, you know that that is more or less impossible. But if you put it in code, it is possible. And so I think you can only truly collaboratively work in data analysis if you do scripted analytics in code and you throw out all the interactive tools, Power BI, Tableau, ArcGIS, and Jupyter Notebooks that I just used for the live demo, because Jupyter Notebooks is also not useful in terms of version control and diffing and merging. So this is the first law of analytics tools. It has to be true because I made it up. If you can easily merge changes from multiple coworkers, and if you can implement automated tests, you can use that tool. If you cannot, you should not use the tool for professional data analysis, in my opinion. What's also part of the professional best practices is testing. I wrote a blog post a while ago about 3 levels of testing in data analysis. You can read that later on if you like. We already saw a very simple type of automated testing with the assert statements. So if I know that a certain value should be always larger than 0, I can say assert value larger than 0 in my code. And if it happens to be 0 or smaller, sometime later your code will stop and it will tell you that this assert statement wasn't met. So that is a very simple and useful way of kind of checking simple things if they work as intended. Then there are unit tests. Unit tests mean you take a more complex part of your analysis code and you kind of wrap it in a function. Then you feed that function with synthetic data, and you test that what comes out is actually what you think your function should do. That is for more complex algorithms. It's also very useful. And I think also that unit tests should be part of any professional data analytics project. And the final thing that you can do is consistency checks. So in unit tests, you check that your code works well on synthetic data. Now, if you have your real data, you don't know the correct result in advance. But for example, you might know in advance that certain ranges should apply to your data. And let me just open my kind of my scripted version of my demo here. In the end, I have an example of such a consistency check. So for example, if I have, so by the way, that's the map of Munich and the schools. Here's the greenest school. If I want to check that my analysis is more or less correct, I could do simple consistency checks on my green pixel data from my schools. For example, I know that I have more than 100 schools and less than 500. I know that the minimum pixel count is more than 10, and it has to be, and the maximum is, this actually should be a smaller than, should be less than half of the pixels in my box. And then I also have kind of a consistency check on the median of my values. If you put checks like these into your analytics pipeline, they don't cost you anything in terms of runtime. But if I screwed up my input data at some point and I only get zeros, this test will immediately tell me. Or if I only get like 100% in each box, this test will tell me. And you will thank yourself in the end if you put these checks in your analysis and they tell you if your things are going as you think they should be going. That was the demo of the consistency check. And that's it from my side. Happy coding. Here's the link to the GitHub repo. I also paste that in in the chat in a minute. And I'm open for any questions you might have.
Thank you very much for this great presentation, Eberhard. It was actually pretty cool, a little bit fast, but I think given the time constraint, it is imaginable. So we have a couple of questions. So looking at the time, I should go right away with those questions. So Marina asks, like, why did you have to split the joined school buildings and didn't do the centroid right away?
Because the thing I get back from the uni reunion, this is called Schools Unified here. If I print that, you see that I get just one multi-polygon. So that is just one shape that consists of many polygons. I can also just display that here. So that is not actually a geodata frame as I like it. It's just one geometry consisting of many small polygons, and the explode part, the explode operation of GeoPandas rips apart all these polygons into kind of separate lines in my table.
All right. So another question is from Alex. So he asks that how was the tree coverage computed from raw data?
That's a question you have to go to the Copernicus website to answer, because I don't know. I just downloaded data from the Copernicus high resolution land cover data set. So sorry, can't help.
All right. Okay, so then there is one other question from Marina, where she asks, what package or tool did you use to generate slides?
Yeah, that of course also in the repo. So the slides are actually defined in a markdown file, slides.md. You can also just view that in GitHub. It doesn't look as nice, but it has also the content. So you can also click the links here if you are interested in the content. And then I pipe that through, that's down here. I pipe that through Pandoc. And Pandoc takes the markdown file and outputs this fancy HTML slide thing. And you have a choice of different frameworks for the look and feel and different themes for the colors and blah, blah, lots of interesting options.
Okay. So there is, I think, a suggestion from Ahmad. On a project of object detection on satellite maps, we believe that better quality maps will improve the detection process. Which API do you recommend to use? Actually, it's a question. So we have tested Zmap, BingMap, Map. Thank you.
Let me just read that again. Better quality maps. Gmap. That's a question I probably couldn't answer, because I would assume that the image quality is pretty much the same between all the different, or you can get very high quality satellite imagery from many different data providers. So it's probably rather a question of the terms of use and the cost rather than the specific data provider. Because I mean, Google doesn't fly its own satellites, I think, but they buy the data also somewhere else. The EU and the Copernicus program, they have like lots of interesting high quality data. Maybe that's a place to look.
All right. So are there any questions, guys?
Yes, will there be a recording of what you presented? I'd like to rewatch.
Yes, definitely. So we are recording it right now, and it will be published in our YouTube video later, as a YouTube video later on. So I will email all the participants with the slides and the YouTube video.
Great, thank you.
Perfect. So is there any other questions? So are there any other questions? No. Okay, then maybe we can move